This is section 5.1, Areas and Distances, content objective 2, which is to use the built-in summation feature of your calculator to compute RAM estimates when n is large. By the time we're done, I'd like you to discuss your other options for completing problems of this type when you can't remember the summation formula. To get toward this, we're going to connect to our old knowledge. We've practiced computing RAM estimates for areas under curves using nice small values of n. But what happens if n gets large? What if n is 20, 100, or even 1,000? The estimate we find will be much closer to the actual area under the curve, which is a good thing. But the bad thing is that computing this estimate one rectangle at a time, like we have been doing, will be incredibly tedious, and our chances of making an error are pretty high. So what can we do? Before we answer that question, let's recall some pattern recognition that we did in our pre-calculus course when we worked with series. And I want you to remember that a series is a sum of sequences terms, and it's often designated using this notation here. We take the first sequence value, then the second sequence term, the third sequence term, and we add them all up, and we do that until we run out. Now, writing a series this way requires a lot of space, and it takes a lot of time to write. So mathematicians who frequently use series tend to do what mathematicians do best. They identify the underlying pattern and represent that pattern using another notation that is more condensed and yet still contains all of the same information. This notation is called sigma notation, and it looks like this. Notice here that our subscript 1, 2, 3 up to n was replaced with an I, and then we have what I is going to begin with and what I is going to end with. Notice, too, with this notation that the sigma is going to be the Greek letter that looks like the E, and it stands for a sum. With this notation, this letter I is called the index of summation, and I will always begin with the number that's placed at the bottom of the sigma, and then it will climb through whole number values until it reaches the number at the top. So in order to complete this objective, we need to be comfortable moving between the two notations. So let's do the easier direction first, which is where we have it condensed and we want to spread it out. If we look at our first one here, we can see that the index starts at 1 and it moves up to 6, and that the index letter I is just what's being added. So if we look at part A, this will simply be a 1 plus a 2 plus a 3. We continue climbing until we get to the 6. If we look at part B, we're going to change the beginning value of our I, and so I will start with a 0 and it goes up to 5. Now hopefully in looking at this, you will notice that we get the same sum with two different sigma notations, and that's going to have some application when we start looking at our sums in a calculus context. We can often have two different sums that represent the same thing, and you need to be able to recognize that they are the same. Here my index is a j, and it's starting with a 3, so my first term will be a 3 squared, my next will be a 4 squared, then a 5 squared, a 6 squared, and a 7 squared. Now what you should notice here is that we did not simplify these terms, and the reason we didn't is we want to be able to see the pattern. We want to see what's the same in every term, and we want to see what is changing by adding 1 over and over. That's going to help us when we start to go the other direction. If we look here at D, n is a variable and k is the index, so it is the k that's going to be changing. So that 1 over n will still be there, whereas the k will start at a 1 and continue on to n. So in this case, because we don't know what n is, the general notation that we would use is we do 3 terms, and then we imply that the pattern continues by using plus dot dot dot, and then we put the last term if it's available. And in this case it is. We'd have a 1 over n times an n squared plus a 1. For our final example, we can see here that this I is an index letter of I, but it's also a subscript of an x. So if I rewrite this, it will be an f of an x sub 1 times delta x plus an f of an x sub 2 times a delta x plus an f of an x sub 3 times delta x plus continue the pattern until the last one, which is f of x sub n times delta x. Now hopefully as you're writing this out, you're going to see that this kind of looks like what we did in our first objective. We have a delta x, which was a width of a rectangle, and then we're multiplying by outputs, which are heights of rectangles. And notice that the heights are coming from different values of x. So this is the notation that's going to be very closely linked to that rectangular approximation method that we've already practiced. Now I'd like to do the other direction where we start with the written out sum and we have to recognize the pattern ourselves. So when we're looking for the pattern, we want to look for what stays the same, and then we want to look for what is changing, because the things that stay the same are going to be the same in the sigma as well, and the things that are changing we will have to represent using that index. So if we look here, we can see that every single one of these terms has a 1 divided by a 3 times something, and that something starts at 1 and then climbs by whole number values. So we can let that be our index and write down that the index is going to start with our first value of 1 and it will end with our last value of 9. If we look at our next one, we can again see that the thing that is the same in every single term is a 5 and a 1 plus, and then the things that are changing are these numbers here, and we can see that we're starting with the 1 and going to 15. So we can let our index be a 1 and climb to 15 and then replace those things that are changing with the I. If we look at this next one, again, the things that are the same are the brackets and the 1 minus and a parenthesis and a squared. And if we look at what's inside the parenthesis, we can see that the 4 and the division symbol are staying the same on all of them, whereas the top is changing, and it's changing with integer whole value jumps. So we can put an I on the top and start with an I value of 1 and end with an I value of n. If we look at our final one, we see that this 1 over n remains the same with every single thing, as does the square root, as does the 1 and the minus, and the parenthesis squared, and as does the n on the bottom every single time. Now if we look at what's happening with the top, we start with a 0, then we go to 1, then we go to 2, so we're climbing by integer values. So we can let that be our index and let I start at 0 and then go up to our final thing, which is an n minus 1. So what does this have to do with RAM? To answer this question, let's consider the following region's area and how we'd compute its approximation using RAM when we have n subintervals. And what's interesting in this setup is that we are going to represent each of these x values using an index, and then we're going to connect that index to what the actual value of that x coordinate would be. So we know that we start with A and we end with B in all of our problems, and we know that we get from here to here by adding one value of delta x, which was that b minus a over n. So in our previous objective, we were able to find delta x at any time. So if we want to label these using subscripts, we could say that this is x sub 0, x sub 1, x sub 2, x sub 3, and we go all the way out to x sub n. And if we want to get the subscripts written in terms of what the actual value is, so instead of writing x sub 1, we want to write what it equals. Notice that would be a plus 1 of those delta x's. And if I want to get to x sub 2, then I would start with my left edge a and I would add 2 of those delta x's. Similarly, if I want x sub 3, then I would have my left edge, which is a, and I'd add 3 of those delta x's to get to it. So I can choose any x sub I and figure out what the x coordinate will be, the number that is assigned to that x sub I, by doing the left edge a and adding I of those delta x's. So by that token, we can end all the way up at b, which was x sub n, by taking the left edge a and adding n of those delta x's. So the goal is to find the pattern and then represent the pattern in a condensed format. So if we think about doing this like we did in Objective 1, our LRAM is going to be our width, which is delta x, times our first function value, which would be f of, if I want to do a left, that means my first left edge in this first subinterval is going to be x sub 0. My next rectangle would be delta x times its left output, which will be x sub 1 plugged into the function, plus my third rectangle would be delta x times f of x sub 2, and I would continue on until my final rectangle. On my final rectangle, my left-hand edge will come from x sub n minus 1 plugged into the function. So I have a delta x times f of an x sub n minus 1. Now if I look for that in a condensed format, I can see that the thing that is the same on all of them is delta x and the f, and it is the subscript that will get the index. And the subscript starts at 0 and goes to n minus 1. Now this is good in terms of recognizing the LRAM, but it's a little problematic if we want to try and compute it, because we don't know what these x sub i's are. So we need to move away from the subscript and move into what that subscript is actually representing as a number. So the other way that I can do it is I can do delta x times f of x sub 0, which is going to be a plus none of those delta x's, plus another delta x. And notice that I've got delta x in all of these, so I'm just going to pull it out so that I don't have to keep writing it. And the next time I will have f of a plus 1 of those delta x's. And the next one I'll have f of a plus 2 of those delta x's. And I will continue the process until I get to my final one, which is f of a plus n minus 1 of those delta x's. So if I want to rewrite this again, I can say that this is the same as the summation of delta x times f of a plus I of those delta x's. And again, I will start at 0 and end at n minus 1. So what about RRAM? With RRAM, we again will have that delta x times a function value plus delta x, which is a width, times a height, plus delta x, which is a width, times a height. And we'll go all the way out to our final rectangle, which will be a delta x times a height. And let's figure out what the heights are coming from. If I want a RRAM, that means in my first subinterval, the right edge is going to come from x sub 1. And if I look at my next one, the right edge is going to come from x sub 2. The next one will come from x sub 3. And my final rectangle, the right edge is going to come from b, or x sub n. So when I condense, it looks an awful lot like the LRAM, except that instead of I starting at 0, I is going to start at 1. And instead of I ending at n minus 1, it will end at n. And again, if we want to replace these subscripts with actual x values, then I'll have delta x, and again, I'll factor that out so I don't have to keep writing it. And I'll have f of x sub 1, which is a plus 1 of those delta x's, plus f of x sub 2, which is a plus 2 of those delta x's, plus f of a plus 3 of those delta x's. And I continue the pattern until I have f of a plus n of those delta x's. So notice if we want to condense this one into the pattern notation, we will have the summation of delta x times f of a plus I of those delta x's. And I, instead of starting at 0 and going to n minus 1, will start at 1 and go to n. The MRAM, or the midpoint rectangular approximation method, is a little more tricky. So before I scroll this picture off the screen, I want to talk about what these midpoints are going to be and where they will come from. If you remember from your old geometry or Algebra 1 courses, you know that you can find the midpoint by averaging the coordinates of any 2 points. So if we want to find this particular value here, we would average this x-coordinate and this x-coordinate, which will be x sub 0 plus x sub 1 divided by 2. We could apply this same rule to any of these subintervals. So let's say, for example, we want to go from x sub I to x sub I plus 1. Well, the midpoint of that one will be x sub I plus x sub I plus 1 divided by 2, and then the output that will be assigned to the function will be f evaluated at that input. Now this works great as long as we're looking for the pattern, but if we actually want to compute it, we need to rewrite x sub I and x sub I plus 1 in terms of delta x and a. So that x sub I plus x sub I plus 1 over 2 is going to be the same as a plus I of those delta x's plus a plus I plus 1 of those delta x's, all over 2, and that will be what's plugged into the function. So if we simplify that, we will end up with an f of 2 of those a's plus an I plus 1 delta x plus another I. That gives us 2I plus 1 of those delta x's over 2. So we're going to use this when we write our MRAM, and we're going to pay attention to the fact that on our first subinterval, that first subscript starts with a 0. And on our last subinterval, which is here, that left edge, which comes first in the summation for the average, is going to stop at an n minus 1. So MRAM will then be our delta x times our first height, which comes from x sub 0 plus x sub 1 over 2, plugged into the function, plus delta x times our second height, which is x sub 1 plus x sub 2 over 2, plugged into the function. We can do our third one, and then we'll continue the pattern until the last one, which, if you recall, was f of x sub n minus 1 plus x sub n all over 2. We can condense that into a sigma notation by realizing delta x is in all of them, f is in all of them, dividing by 2 is in all of them, and if we choose to let this subscript be our I, then this next subscript will be I plus 1. So I will begin with 0, just like on the LRAM, and it will end with n minus 1, again just like the LRAM. Problem with this, though it helps us recognize the pattern and see that it's an MRAM, it doesn't actually help us compute anything because we need to know what x sub I and x sub I plus 1 really are. So that's where the work we did right before this comes into play. We remember that x sub I is a plus I of those delta x's, and x sub I plus 1 is a plus I plus 1 of those delta x's. So if I simplify, I'll get delta x times f of 2a's plus 2I plus 1's times the delta x over 2, and I starts at 0 and goes to n minus 1. The beauty of this is that once we see the pattern and we can represent it using sigma notation, then we can use our TI-89s to automate the process. So if we can write it in sigma, then we can just plug it into our calculator and it will compute the RAM approximation for us. So the first thing we'll want to do when we're doing this process is we'll want to enter our function into y1. Then we'll need to compute our delta x. Then we're going to start typing it into our calculator. So let's run through these 4 steps with this first example. We want to compute LRAM on the interval from 10 to 20 when n equals 50, and this is our given function. So our first step is to put this f of x into our calculator, which you can see I have done here. 2x squared plus 3x plus 4 is stored in y1. Our second step is to compute delta x. Well, in order to compute delta x, I need to know my b minus my a over my n. So my b is 20, my a is 10, and my n is 50. So I end up with 10/50ths, or 1/5, or 0.2. So that is my delta x. And I want to write LRAM using the pattern. So LRAM is going to be my delta x, which is 0.2, times my function evaluated at x values that are my a, which was 10, plus multiples of my delta x. And remember, on an LRAM, that my first left edge does not add any of those delta x's. So that means I is going to start at 0 and end at my n minus 1. So this is what I'm going to put into my calculator. I'm going to access the sigma notation, which is F3 Calculus menu, number 4, and then I'm going to type it in just as it's written. So let's go through that so you can see how it works. Here's my Y1. On the home screen, I'm going to go to my Calc menu and choose the sum, which is number 4, and then I'm going to type in 0.2 times my function, which is stored as Y1, of my x sub i's, which will be my a plus my alpha I times my delta x, which is 0.2. So in this sigma notation on the calculator, I need to enter the exact same, or all of the information that I have in the written out sigma. So I've written the sigma, that's typed into the calculator. I have the innards. Now I need to tell it what the variable is and what that index is going to start with and end with. And all of those are separated with commas. So I'll do comma alpha I, comma 0, comma 49. Then I close the sigma notation, hit diamond enter, and my answer is 5093.8. With part B, we're going to do the same process. We're going to let y1 of x equal that function. We're going to compute our delta x, which is b minus a over the number of subintervals. And then we're going to set up our sigma notation. Sigma notation is delta x times output. So we've got a width times a height, and in that height we're going to put our x sub i's. And our x sub i's, because we're doing right edges, it's an RRAM, that I is going to start at 1 and end at n. And x sub I for any I will be our a, which is negative pi, plus multiples of our delta x. So now our job is to put this into the calculator by storing f into y1. So pull out your calculator. Notice that I have 2 plus sine of x in y1, and I'm in radian mode. I'm going to go to my home screen, access the sigma, which is number 4 in the calculus menu, and then I'm going to type in the innards of that sigma, which is 2 pi divided by 25 times the function outputs, which will be y1 of my a, which is negative pi, plus multiples of my delta x. Once I have the innards of my y and the innards of my sigma, I have to tell the sigma what my index variable is, separated with a comma. And then I have to tell it where that index will start, which is 1, and where it will end, which is n, or in this case, 25. Hit diamond enter to avoid the desire to give me an exact value, and I get 12.566. For our third and final example, we need y1 to equal that log natural of x minus 2. We need our a, which is 3. We need our b, which is 8. We need our n, which is 10. We need our delta x, which is b minus a over n, which is 5 over 10, which is 1/2 or 0.5. And then we're going to write our MRAM, which, if you recall, is the sum of our delta x times our function values evaluated at midpoints. And the midpoints were x sub I plus x sub I plus 1 over 2. So that's going to be a plus I of those delta x's plus a plus I plus 1 of those delta x's all over 2. So in this particular case, and our I starts with 0, remember your first left edge up to your last left edge. So if we rewrite this using our A's and B's and delta x's here, we're going to have the summation from I equals 0 to n minus 1, which is 9, of delta x times f of 2 of those A's, that's 2 of these 3's, plus 2 I's plus 1 times my delta x again, all over 2. So this is what we're going to want to put into our calculator. So notice here in y1, I've put log natural of x minus 2. And on the home screen, it's going to be kind of tricky with all the parentheses. So you might want to pay attention, then pause it and try it on your own. So we will do F3, 4. We're going to do 0.5 times y1. And we're going to start y1. And then we're going to start the top of that fraction. So 6 plus 2i's plus 1 times the delta x, close the top of the fraction, divide by 2, close what's inside y1, then tell the calculator what the index variable is and where the index starts and where the index ends. Close it off, diamond enter, and we get 5.759.